Hello, good afternoon, and welcome to the Veolia Hybas Proven Process Intensification of CAS plants. We'll be starting in a few moments as we wait for some further attendees to join. Please bear with us. Hello, and welcome to the Hybas Proven Process Intensification of CAS plants presented by Veolia. Your presenter today will be Danielle Lamar, and myself, David Pierce, will be your moderator. Some webinar notes. You should be able to hear me speaking now. There are two options for audio that you can connect with. Please, though, if you are not hearing it through your computer, please do not call in on the phone. Also, your microphone is automatically muted so that there's no feedback. During the live webinar presentation, we will be having an interactive Q&A. So on the right-hand portion of your screen, you'll be able to ask questions using the panel. Please feel free to submit those questions throughout the presentation, and we will do our best to answer all of them within the allotted hour time frame. Along with today's live webinars, we will also be hosting several others in the coming weeks and months. You can find the information on those and when they will be at our website, veoliawatertech.com. As well, on that site, you will be able to download previously taped webinars that you can watch on demand at your convenience. Following the presentation, within 1 or 2 days, we will be sending out a certificate with your name and your participation of today's webinar. At the end of today's webinar, we will also be sending you a short survey. We look forward to your feedback, and all participants who do fill out the survey will be entered into a draw to win a $25 Amazon gift certificate. So please feel free to fill it out. It should only take a couple minutes. Veolia Water Technologies, we focus on key areas, so technologies that are advanced and robust water treatment technologies with extensive line of standard equipment. We also focus on projects of engineering and procurement of advanced water treatment projects, and we have a wide range of services for operational enhancement at water and wastewater facilities. Today, we will be hearing from Dan Lamar, who is an employee of Veolia Water Technologies Canada. Dan graduated from École Polytechnique of Montreal in chemical engineering in 1994, and also has a master's degree in environmental sciences, also from École Polytechnique in 1996. Since graduating, Danielle has worked in the biopharmaceutical field, as well as for different water treatment system manufacturers. This brought him to work on both drinking water and mainly wastewater treatment for both municipal and industrial projects. His position brings him to work on R&D activities, introduction of new technologies to the market, and process engineering on full-scale projects. Daniel has been working as a process engineer for the last 20 years for WWTP in Montreal. So without further ado, I will allow Daniel to begin the presentation.
Good afternoon, everybody. So today's presentation, we don't have that much time, so a limited number of subjects. So really introduction to the Hybas system, which is what we're presenting here as a process intensification technology. This being supported by a few case studies and some design considerations, general design considerations, before reaching the final conclusions, and then question and answers. Hybas was developed and is proposed in link with activated sludge systems. So activated sludge system is known, has been known for more than 100 years now. It's there are thousands and thousands of plants operating everywhere, and operators are trained to monitor and adjust all of these parameters: mix flicker, SRT, F2M ratio. Pretty well-known technology. Their main drawback being that your sludge concentration cannot reach more than a few thousand milligrams per liter, and the limitation being the secondary clarification, which means that if you want to increase capacity of an existing system, you will end up building larger tanks to get your system up and running, especially if you want to aim for nitrification, and especially in cold water conditions, which means large and costly footprint for greenfield or even for expansion projects. And that's where Hybas can be used. So when you get to expansion of an existing activated sludge system, the first thing that comes to mind is, well, let's add a parallel treatment line to the ones that we have already, which means lots of footprint and lots of cost for construction. A new trend on the market since a few years is hearing the word process intensification. So the goal being to try to do more within the existing tanks that are already there and already quite large and built since many years. So the goal is to increase the biological activity in your system to treat more pollutant within the same volume. And there are really two main ways to do this. First one being to add a biofilm within the existing aeration tank. This biofilm supporting new biomass or additional biomass than the suspended growth biomass of your activated sludge. And another option to intensify the process is to add a better clarifier that will be able to handle more mixed liquor concentration than the usual secondary gravity secondary clarifiers. And as an example, the first example would be using an MBBR, so a perfect secondary clarifier allowing to increase your mixed liquor and SRT. So that also works. So the Hybas, which is this number one option here to add biofilm within the activated sludge. So Hybas stands for hybrid activated sludge and is also known as IFAS on the market. And the Hybas is just the trade name for the IFAS by Veolia. And it's actually a very simple process. It's simply adding MBBR carriers within an existing activated sludge aeration tank. I'm saying existing, it could be a greenfield also, but within an activated sludge aeration tank. So that goal would be to increase the nitrifying biomass in that reactor without increasing the mixed liquor concentration. So after implementing an Hybas system, your mixed liquor will remain the same, a few thousand milligrams per liter, just same as before. However, you have now a biofilm growing on the MBBR carriers, along with suspended growth biomass growing as the activated sludge. Some important notes here. The nitrifying bacteria, they like to attach to a hard surface and grow as a biofilm. It's in their nature. They preferentially attach to MBBR carriers. So getting nitrifiers to grow, attach and grow on a fixed media is not a difficult task. And as soon as you get nitrifiers to grow on a fixed solids area, then, and if you can keep that fixed solid area within a reactor, then there's no risk of washing out these nitrifiers from the reactor. And the third thing to keep in mind is that if you manage to get biofilm growing on this MBBR media, the biofilm will grow over time. Eventually, the thickness of the biofilm will be such that it will start to detach slowly as a self-regulated process. And this detachment of biofilm will generate natural bioaugmentation of your mixed liquor. So at the end of the day, after adding this MBBR media in your aeration tank, you will end up with nitrification being generated from the nitrifiers growing on the biofilm, but also from the nitrifiers growing in the suspended phase through bioaugmentation from the MBBR detachment. One thing important for operator is that at the end of the day, they will see almost an identical activated sludge system as they had before. So in terms of operation, there will be very, very limited implication for the operators. So familiarity will remain for the operators. It's not a new technology for them. It's really more of the same. The core mechanical elements of an Hybas system is very limited. It's basically three of them: media retention screens, and an aeration grid. I'm adding here, I have a fourth item, aeration blowers. Of course, you need an air blower to provide air to the aeration grid. But the main components of the Hybas is really these first three. So the media, of course, the most important part of the Hybas, the sieves used to keep the media inside of the reactor, and the aeration grid to provide aerobic conditions for growth of the biofilm. The media that we're showing here is the Annex Colness K5 media, virgin, and then after being fully seeded. These guys are roughly 1 inch in diameter, 25 millimeter, and about 4 millimeter thick. And they provide a very high surface area, protected surface area. So the surface area available for growth of the biofilm is about 800 square meter for each meter cube of bulk media volume. The second item, the screens, the media retention screens, they're made out of perforated plate built into cylindrical construction. They're designed to generate a limited head loss, and we sometimes use air scour piping to push media away from the screen assembly and to keep the hydraulic up and running through the Hybas. And then the aeration grid is very simple. It's a perforated pipe medium bubble aeration system. Its main characteristics being that it is maintenance free. It is very rugged, and it's most probably mechanically over designed, and that's the way it's supposed to be, because these aeration grids are designed to be in operation for tens of years without operator intervention. They are designed as a full floor coverage. We don't want to generate roll patterns, which would reduce oxygen transfer efficiency. So it's really full floor or almost full floor coverage. And usually 304 stainless steel, sometimes 316 under, mainly for industrial applications. So why is that Hybas system so efficient and interesting for increasing the nitrification capacity of an activated sludge? So first off, we need to go through a little bit of how these activated sludge systems are designed when nitrification is needed. So at the activated sludge system, one of the main design parameters is for sure the SRT, the sludge retention time, solids retention time. And we know that nitrifiers are slow growers, and especially at low temperatures, their kinetics will be quite low. Modeling can show that SRT that needs to be respected, under which if you're designed lower than the minimum theoretical SRT, you are in a washout condition. So you will waste more nitrifiers than you are growing, which will result in having no nitrifiers in your activated sludge, in your suspended phase anymore. So that's a condition you want to avoid. By adding MBBR media in your bioreactor, what we're actually doing is we're decoupling the nitrification from the suspended growth. So nitrification is now controlled by a biofilm, which is physically maintained inside of the bioreactor, while the suspended growth is decoupled in terms of SRT from the nitrification, which means that the bioreactor can now be designed at a low or very low SRT, even lower than the SRT needed for nitrification, because nitrification is now supported by the biofilm. And that results in a much smaller aeration tank, or in an aeration tank that has more capacity for a given volume. So if you go back to that curve here, the red or brown curve here is the minimum theoretical SRT. So you are not supposed to design for this, because you will get washout as soon as you get a little upset. And normally you will design for an SRT of about 2 times the minimum theoretical SRT. But then when you work with an Hybas system, you can reduce this design SRT significantly. And here the black dots are some examples of some North American Hybas plants. Their design SRT, and you see that some of them are even lower than the minimum theoretical SRT, which means if these guys didn't have any MBBR media, there would be no nitrification happening in these reactors. Yet, because of the Hybas system, nitrification is happening without any issue. And the impact on the reactor volume is significant, while a conventional activated sludge system would be designed for 14 days SRT, as an example, giving 10,000 meter cubes of reactor volume. An Hybas system designed for the same effluent requirement, the same nitrification capacity, would be designed at 5 days SRT, and a reactor volume that's about 1/3 of what the CAS system is. So it is a major process intensification system. Some additional benefits of the Hybas, apart from increasing the nitrification capacity, is that it showed that it does impact somehow the SVI, the sludge volume index. So you get a better clarification or a better sludge quality in terms of clarification. It's not drastic, but it is significant still and measurable. And I must also add that this Hybas system can be implemented within any activated sludge configuration, either fully aerobic, MLEB, or whatever. So Hybas is a fully proven process intensification, and that's probably a very important topic here. The buzzword of process intensification has been around since a few years, even though the Hybas has been around for about 20 years. So process intensification is not the new kids on the block. It was already discussed 20 years ago, and there is a solution implemented since 20 years that can do this process intensification. So the first MBBR plant dates back from 1990, and then the first, that was a pure MBBR without the activated sludge part. And then MBBR combined with activated sludge. First plant is in operation since 2002. And we have a case study on this one in the next few slides. Nowadays, we have more than 60 Hybas plants worldwide and more than 1,000 pure MBBR installations just within the Veolia world. We have 35 Hybas plants in North America with sizes ranging from very small to very large. Here in Canada, we have two of these Hybas references. The first one being Hawkesbury in Ontario, which is a medium-sized activated sludge plant, which was a retrofit of an existing activated sludge system. And the second reference, which is currently in startup, is the South End plant in Winnipeg, which is a much larger plant, 125 MLD as an average daily flow. And this one was a greenfield BNR activated sludge system. Now with the case studies, the first one presents the first Hybas reference worldwide, which is Broomfield in Colorado. So the plant that was there in 2000 was an activated sludge system, but then new effluent requirements needing much better nitrification along with total nitrogen removal, along with increase in flow and loads, meant that the existing activated sludge system was just too small to meet these new conditions. This plant was upgraded. Well, they had two choices: either build more tankage or do more within the existing tankage, which is the way they decided to go. So the plant was repurposed, the existing bioreactors repurposed into a series of different tanks with some denite activity, and then two trains of Hybas, so mixed liquor with MBBR media, with each Hybas reactor divided into two reactors in series, and then the usual RAS and some internal mixed liquor recycle to optimize denitrification. So some graphs showing some of the results. So this graph from 2002, so during construction period, that shows that under summer conditions, the existing plants didn't have much problems with nitrification. Ammonia here was below 0 and 5 probably in summer. But then as the temperature of the water drops during fall conditions, nitrification would be slowly lost until they would get to almost no nitrification in winter condition. And right about that time, the Hybas plant was ready to go, and they started adding media each week, adding more and more media, and that media getting seeded slowly. And after a few weeks of operation of the Hybas system, adding more and more media, even though the temperature remained low, because we're here in middle of December and even beginning of January, ammonia just fell within a few weeks to almost non-detect. And it's really this addition of the media that made the difference. And with even the influent ammonia slowly going up. And as a final results, having full nitrification with the Hybas addition. With only 30% media fill. That number can go up to 60% if you add more and more media within your bioreactor, your Hybas reactor. Some other interesting graphs here, impact of SVI. So this is a trend of about three years of operation, showing that the SVI was controlled during all that time to about 120, which is very good. Some data shows that before the Hybas retrofit, this SVI was more in the 150 order of magnitude. So there was a clear benefit on the good side of things by adding the Hybas system. The design SRT went down significantly. So after Hybas addition, we're at an SRT of about 3.5 days, which would normally be on the low side to support nitrification. Be aware that this plant here in Broomfield does not see very cold water in winter time, with lows in the about 15 degrees Celsius as a monthly average. But even that was enough for them to lose nitrification in the colder months. And you can also see that the mixed liquor concentration in that case was on the low side, about 2,000 milligrams per liter. Again, the impact of SVI. So that's a better graph to show before and after Hybas being in operation. So before the Hybas, SVI, the average of 50% average was about 150 and went down in year 2003 and 4 to about 135. So not a drastic difference, but still a significant difference in the right side of things. And one final operation results that shows that before this Hybas upgrade, the plant would have sporadic nitrification. So ammonia removal efficiency between 20 and 100%, but scattered all over the place. While just after adding the Hybas, implementing the Hybas, the nitrification efficiency was very consistent and stable, close to the 100% with effluent ammonia, as we saw earlier, in the 0 to 2 milligrams per liter in the effluent. We're trying to show here in this graph, it's don't be afraid of it. There's lots of color, but it's not that scary. We're trying to show what's happening really on the media itself, on the MBBR media, throughout the different seasons in the reactor. So we have here in black the water temperature that oscillates between summer condition and winter condition. And then the mixed liquor concentration, which remains more or less constant around the 2,000 milligrams per liter maybe. So there's no link between MLSS and water temperature. However, we're also showing here the biofilm thickness, or the biofilm, the amount of biomass on the biofilm expressed as gram of biofilm, total solids, per square meter of MBBR media area. And we show that, keep in mind, we have two Hybas reactors in series, reactor 1 and 2. So the first one sees a lot of ammonia. Reactor 2 really does polishing, so does not see much ammonia. So this reactor 2 is really substrate limited. And as expected, there is much more biofilm growing in the first Hybas reactor as compared to the second one. But we also see that there's a seasonal shift in the biofilm thickness, with marginal media biofilm on the media in summer condition. We see it very well here. There's a very limited amount of media, because most of the nitrification is simply happening in the suspended growth phase. As we were mentioning earlier, in summertime, the activated sludge system does nitrification without much issues there. So there's very little biofilm because there's not much food for the biomass to grow on the media. But then when you get to the winter conditions, nitrification barely almost stops in the suspended growth, and most of it is now happening in the biofilm, which grows and grows until you get to the thickest biofilm. And you can see that some of the ammonia leaches into Hybas reactor number 2, which also leads to some growth in that second reactor. And as a effluent summary for that Broomfield plant in the last 15 years, we have an effluent ammonia of about 0.3 milligrams per liter. So that's the #1 parameter for our Hybas design, because keep in mind our Hybas design is only used to boost nitrification here. So the rest of the parameters, total nitrogen or NOx, even TP, is linked with the design of the rest of the activated sludge system. Our second case study, this one will be much faster, but we wanted to show a local Canadian reference here. So this Hawkesbury plant, which is located about midway between Montreal and Ottawa. The existing plant back in 2013 was non-compliant in terms of effluent ammonia, and was also at capacity in terms of BOD and TSS removal. So plant upgrade, there was 4 options that were on the table. First one was to do nothing. That was not really an option. But then second option was just expand the existing activated sludge and build a new train. There were 3 trains existing, so they would have to build a 4th or even a 5th train in parallel. They could rebuild the whole plant because it was an old plant built since probably 40, 50 years. So they could rebuild the whole thing. Or if they wanted to make this simple and to save money, they could just retrofit the existing aeration tanks into an MLE process, which is the way they went. So the 3 trains of primary, bioreactor, and secondary clarifiers were all retrofitted. It used to be 1 big aeration tanks. Each tank was repurposed into an MLE, so pre-anoxic, followed by 2 aerobic zones. First of the 2 aerobic zones was the Hybas reactor, followed by a second aerobic zone, which is media free. So just an aeration suspended growth bioreactor here. So some pictures of this. So you can see this first anoxic zone, no air bubbles, and there is a weir feeding the second reactor, which is the Hybas reactor. So a weir is a very good way to go. You don't want the MBBR media to crawl back into your anoxic reactor. And it also ensures quite an even flow distribution throughout the width of the Hybas reactor. So that's a good way to do it. And then your Hybas reactor, not a very big one, the coarse bubble aeration grid, the media retention sieves, and you can more or less see the millions of pieces of MBBR media in suspension in that reactor. And then you can see the big here the 3rd reactor, so the last of the bioreactor train, which is basically just an aeration tank with fine bubble diffusers. And this, what is this tank doing? Well, it's doing mostly nitrification. Keep in mind that we have detachment of the biofilm from the Hybas reactor. This biofilm is a nitrifying biofilm. Once it's detached, it gets mixed in within the suspended growth, the mixed liquor. So that means bioaugmentation of your mixed liquor that suddenly starts to nitrify. So that's what this tank is doing. So nitrification of, well, remaining ammonia out of the Hybas zone. Our last section of the presentation is some design considerations to keep in mind when you go for a Hybas retrofit. not so much for greenfield plants where you will not be in those catch-22s usually. So this is mostly applicable to Hybas retrofits of existing activated sludge systems. So the MBBR media is suspended in the mixed liquor. That's what we said since the beginning. If there was no aeration or any mixing, all the media would travel with the mixed liquor, with the water, and would reach the sieve side of the Hybas. In the Hybas, we have aeration, the strong aeration from this coarse bubble aeration system, which also provides mixing. And that mixing energy prevents the media migration to a certain extent. So what you want to avoid with your Hybas is all of your media to migrate on towards the sieve sides and to accumulate on the sieves and eventually pile over the sieves. And eventually you could even end up losing some of that media, overflowing media over the freeboard of the bioreactor. So that's something that was learned the hard way in the first references. What are the limits of the Hybas in terms of hydraulic to prevent this media migration? And one of the key design parameter is the frontal velocity that needs to be limited to prevent media migration. When we're referring to frontal velocity, it's really the velocity of the water by just using the flow in meter cubes per hour through the reactor divided by the cross-sectional area. So side water depth times the width of the reactor, and that will give you meters per hour. So the velocity of the water, and it's also the velocity of the media in that water. So you want to keep that velocity as low as possible to prevent this media migration. Another concept to keep in mind is that in a Hybas reactor, you need to design for the worst case hydraulic condition, which is usually something like the peak influent flow of what, 200% of your average daily flow, sometimes even more than 200%. You need to consider the RAS, which is usually about 100% Q. Some internal mixed liquor recycle to 300%, which means that the total flow reaching your Hybas reactor can reach, well, can be pretty high, up to 500, 600, 700% of your average design flow. And that really is your worst case condition that needs to be considered. And your frontal velocity must be calculated on this worst case flow condition. And that's why process engineering is very important when you do these retrofits. And believe me, some of these were learned the hard way. And these concepts can't really be tested at lab scale and needs to be tested in full scale. Over the last 20 years, that's what has been happening with Veolia. And I can say that most of the errors that can be done in terms of hydraulic has been done in the first years and in the first references. And experience is a very important concept when you get to these Hybas retrofit hydraulic considerations. So let's look at the real example for the Oxford plant in UK that we're considering in Hybas retrofit of their existing activated sludge system. The problem they have is, was that their existing plant was a plug flow multiple pass system. And if you simply say that let's take part of one of the aeration reactor, aeration zone, and retrofit it as an Hybas reactor, you will end up with a flux or in their case of 127 meters per hour at peak flow. And that is for sure a catastrophe in planning. That would lead for sure to media migration. So media would all accumulate to the back end of the reactor and never go back to the inlet of the Hybas reactor. So that would not work. The way to make this work, though, was to use imagination and creativity. And this concept has now been used in several Hybas retrofits. And the solution was to, rather than try to use a frontal feed of the system, as shown here, is to rather use a cross-sectional feed of the Hybas reactor. So have a feed channel on one side and to feed the reactor in the width rather than in the length, and to have a effluent collection channel on the back end of the Hybas that would feed the final aeration zone. And in a full-scale application, what that means is what they did there in Oxford. So they just dismantled part of that division wall that was part of this channel flow. So that division wall here, so part of it was removed to make this a wider Hybas reactor. And on the one side, we have, well, it's shown here, the feed channel with V-shaped overflow weirs to ensure even flow distribution throughout the width of the reactor. And on the other side, the media retention sieves with the effluent collection channel. And be careful there, we're turning the reactor around, so the feed channel is now on that side in that picture, and the effluent channel is on the other side. And you can see here this flow of mixed liquor through the feed weirs just to ensure even flow distribution throughout the width of that reactor. And now the cross-sectional velocity is less than 20 meters per hour, which is totally acceptable. And that was a successful Hybas retrofit. A second important design consideration is head loss impact. So head loss within a bioreactor in a conventional activated sludge is quite limited. Adding Hybas reactors will increase the head loss. You normally want to see a flow distribution system on the feed side to try to feed more or less evenly the mixed liquor throughout the width of your Hybas reactor. You also must account for some head loss through the sieves. And if you have two reactors in series, then you have 2 times that head loss through the sieves, resulting in a total head loss through a single cell Hybas system of something like 100 to almost 200 millimeter, and a little more if you get to the 2 reactors Hybas system. So that's something to keep in mind. It will increase slightly the head loss within the bioreactor. We're now to the end of the presentation. So as conclusions, we can say Hybas is a fully proven process intensification technology used since more than 15, almost 20 years now. 2002 was the first reference. It is used to promote nitrification in any activated sludge configuration. It allows nitrification at low SRT and at cold temperature. And so this is quite important. It's especially well suited for cold water conditions where you can easily wash out your nitrifiers if you don't have this biofilm in your activated sludge process. It also allows phasing of expenses by adding media over the years. So you don't have to design your Hybas system right away for the loads, the ammonia load in 30 years from now. Your bioreactor can be, or concrete work can be designed for this, but you can only add the media that you need to face your existing needs and simply add more MBBR media as the loads, the ammonia loads increase on your system. Very, very simple in terms of operation, maintenance. So no maintenance of the system, no replacement of parts or replacement of the media. The first MBBR reference, as I mentioned earlier, is in operation since 1990 and is still using the same carrier, the same MBBR carrier that was installed 30 years ago. It has Hybas has a positive impact on SVI. There are some design challenges like any technologies. The good news is these are fully known, and these are mostly hydraulics, and the solutions are most usually possible. So we invite you to contact us and see what is possible for your specific conditions. Keep in mind it will generate some head loss in the bioreactor. So if you have zero head loss available, unfortunately, unless you add a pump station, Hybas may not be a possibility, but in any other condition, Hybas is most usually a potential solution. With that, I thank you for your attention, and we will gladly take any questions and maybe comments if you have any. And of course, don't forget to fill in the survey and win that $35 certificate.
Thank you, Dan. So that does conclude Daniel's presentation. We have a lot of questions, so I thank you for the participants in putting those onto the question board. Dan, the first question refers back to slide 13. Is it possible to upgrade by using the two options at the same time?
If we are referring to MBR, the answer is probably no, because your MBR is designed with a significantly long SRT to keep the sludge quality to prevent clogging of the membrane. So you will design usually your MBR for an SRT of between 15 to 20 days, and this will be a nitrifying MBR. And at the same time, you want to make sure that you nitrify everything upstream of your MBR to prevent biofouling of the membranes. And at the same time, it technically would be feasible, but it is there's no real reason to do it because your activated sludge will nitrify within any MBR system. And keep in mind, there's no risk of washing out really your biomass, your mixed liquor with the MBR, unless you just waste lots of sludge. So in theory, the answer is yes, but in practice, the answer is probably no.
Thank you. There are a lot of questions, so if we don't have a chance to answer them in the forum today, we will contact you directly and provide you with written answers. Dan, the second question, referring to slide 36, are there any installations where existing aeration systems, grid and diffusers, remained in service after upgrading to Hybas, or is it necessary to replace the existing aeration grid?
It is necessary to replace the existing grids unless the existing grid is a coarse bubble maintenance-free air diffusion system. So if you're talking existing fine bubble diffusers, you will want to remove them, not because they're not efficient. The only reason is they need maintenance. So fine bubble diffusers will need to be maintained every couple of years. Keep in mind, in your Hybas reactor, you have 50% of the tank volume is used by the media. If you drain your reactor, you have 50% of the volume that is MBBR media. So imagine how much shoveling you need to do to reach these diffusers. So no, you don't want to use fine bubble diffusers with MBBR. And at the same time, keep in mind also that the oxygen transfer efficiency of these coarse bubble diffusers we use with the MBBR is not bad. It's somewhere between a coarse bubble and a fine bubble diffuser because the media in the reactor used as packing, that will increase the oxygen transfer efficiency. It breaks air bubbles, it increases the gas retention time in the reactor, with an overall significant positive impact on oxygen transfer efficiency.
Which leads into the follow-up question of what is the percentage of media in the Hybas system?
So maximum is 60%. When you get to more than 60%, the limitation is the mixing of the media, and you will start to have difficulty mixing and keeping the media fully mixed and in suspension in the water. And if you have a peak hydraulic condition, this media that does not mix very good will tend to migrate more towards the end. So we try to limit the media fill to about 60%. And on the other end, there's no real minimum. You could start with, we have one reference in a landfill leachate where we have 5% media fill, and that works good.
The next question, my understanding is that the MBBR system operates at a higher DO, 4 to 7 milligrams per liter, to achieve nitrification under cold water weather conditions. Would the Hybas process also need to operate at a high DO?
Yes and no. Actually, it's not a need, because you could operate an MBBR system at 2 milligrams per liter. It will nitrify. It just needs to be large enough, though. So being a biofilm system, the limitation in the nitrification kinetics is mostly diffusion limitation of the oxygen throughout the biofilm. So when you increase your bulk liquid dissolved oxygen concentration, you will get more penetration of dissolved oxygen in the biofilm, which will boost nitrification kinetics, which is why usually the MBBRs and Hybas systems are designed with higher DO concentrations, which helps keeping the reactors smaller. I would say that the usual cold water or winter design DO for a Hybas is probably around 4.5 milligrams per liter, but not in the 7 milligrams per liter range. It's lower than that.
The next question, since we have a few minutes left, could you please comment on the management of media during low flow situations?
Dave, I will need you to repeat that, because there was I just lost you for a few seconds.
Could you please comment on the management of media during low flow situations?
Low flow is not an issue. The reactor is fully mixed, CSTR. Under low flow condition, you just have your aeration system still in operation. There is a minimum airflow that you want to keep in your reactor to make sure that you have sufficient mixing to prevent dead zones and to keep the media moving at all times. So that's a minimum airflow that is set at startup, and then you can modulate the airflow to the Hybas anywhere between the minimum to peak flow. And so in low flow conditions, the air requirement will reduce significantly because the ammonia load will be much lower. So you will reduce your airflow down to eventually to the minimum you can go. The airflow being controlled through a dissolved oxygen reading, and ideally along with an online ammonia sensor. So you could have cascade aeration control to really optimize your energy consumption or air blower horsepower consumption throughout online instrumentation.
Can Hybas be used for enhanced BOD removal?
The answer is probably no, because the suspended growth activated sludge does this pretty well. And there's no real limitation to this. So you can design your activated sludge system at 4 days SRT. It will not nitrify, it will remove your BOD easily, and your limitation will just be your secondary clarifier. And even if you were to add MBBR media, you would end up with most of the carbon being removed by the suspended growth, and not much biofilm growing on the media. One solution, though, could be to add a small MBBR reactor upstream of the activated sludge system if you really are running into a carbon removal issue, which is called what we refer to as a BAS system. So it's an MBBR upstream of the activated sludge, which could help with BOD removal. But then usually the limitation will be the solids loading on the secondary clarifier.
What is the best way to denitrify?
Best way is most probably pre-denitrification. So you want to use as much of the available carbon as you can. So you will want to recycle your nitrates, ideally not from that directly from the Hybas reactor, as we were mentioning earlier. Let's use this slide here. As we were mentioning earlier, the Hybas reactor, let's see here, the Hybas reactor is usually operated at a higher dissolved oxygen concentration to boost nitrification, say 4 up to 5 milligrams per liter, even maybe 6 milligrams per liter in peak conditions. And you don't want to recycle that much oxygen in your pre-denitrification tank if you can. So ideally, you would have this Hybas reactor followed by a simply aerobic reactor, just like they have in Hawkesbury. This aerobic reactor could be operated at a much lower DO, say 1 milligrams per liter, and that's where you would recycle your nitrates from.
Okay, Dan, I think we have time for one more question. Is there a difference in energy consumption between IFAS and CAS?
That's a good question. The answer is probably it is case specific. So we are running the Hybas at a higher oxygen concentration, dissolved oxygen concentration. And the oxygen transfer efficiency is not as good as fine bubble diffusers. So if you were comparing exactly apples with apples, then the airflow requirement would be higher with the Hybas. On the other hand, your Hybas is now running at a significantly lower SRT as compared to your CAS system. And this lower SRT will mean much less hydrolysis and a significantly reduced AOR. So overall, it's case specific, and these two parameters are one against each other. The net results will be somewhere in between. So there's no single answer to this, but it's the balance of the lower SRT against a somehow lower oxygen transfer efficiency.
Thank you for the answers, Dan, and thank you to our participants for joining us today on the Hybas proven process intensification of CAS plants. As a reminder, please fill out the survey for a chance to win a $25 gift certificate. You will also be receiving a certificate of participation in 1 or 2 days, and this webinar will be posted to our site, veoliwatertech.com. Thank you once again.